All right, so your hint was you know a root. So it's always helpful to talk about what we know and what we're trying to find out. We know what? What do I know? Well, -3 is over here. Do you see a root there? -1 is a root.
It's like the thing next to -1, the negative like 1 point something also a root?
Absolutely. But here's the thing. Do you know it? No. Like, you could estimate it, but we know -1. It's for sure -1, right? This is definitely a root, and this is definitely a root. But what must they be? Well, imagine, I mean, they wouldn't exist at all. Maybe not a square root, maybe a square root, but they can't be whole numbers, right? Think about it. If you had to estimate this, it's 1.707, right? This is -1.5, right? So they're not as helpful as the root we really know, because we just would have to guess those. Well, we'll find them later. We need to find them. We were told to find them, but there's one that we already know for sure, and we're going to work with what we know for sure. So, because if we know a root is -1, we also know something else. What else do we know? If you know a root, you know a factor. So, what's our factor that we know? Bingo. What's the factor that we know? Well, the root is -1. X plus 1. Okay. So we're starting to shape this up here. So what we actually know, and I'm going to spill over here because spoiler alert, we're going to do that problem on the bottom, so don't have to worry about that. All right, so what I'm discovering here, like this is why it's important to understand what we're doing and why we're doing it, right? What I've just discovered is that 6x to the third plus 5x squared minus 16x minus 15 equals x plus 1 times something, right? We don't know what that something is yet, but we do know that x plus 1 is a factor. So that means x plus 1 times something must be the thing. Now, this is why I always like to use that example 6 and 2 and 3, right? If you knew 6 equals 2 times something, and you just forgot what that something is, what could you do? Divide. You'd do 6 divided by 2, and you'd get the something, right? Well, we don't have that. What do we have? We have all of this equals this times something. So how could we find that something? Synthetic division. We divide, right? So I'm going to take that -1, and I'm going to go, okay, 6, 5, -16, -15. And what do I actually know that remainder is going to be?
Hopefully 0.
Well, it better be 0 or I made a mistake, right? Because we actually confirmed via the graph, this is a root, this is a factor. We're not actually interested in the remainder right now. Sometimes we do the synthetic division to find the remainder, to find that output for an input. Sometimes we want an answer from our synthetic division. We want the division part, right? And that's what we're doing now. All right, so bring down the 6. -6. -1. 1. -15. 15. 0. Now, that part we already knew was going to happen, right? But what else did we discover here? The other factor. Where's the other factor?
It's x. It's 6.
Yep. This is my other factor. I've begun, remember, we're trying to factor here. A lot of times we use strategies like grouping or GCF, but we can use synthetic division. We talked about that very early on. You can use synthetic division factors. So, okay, that means this is actually times 6x squared minus x minus 15. And if we're trying to find a root, we would set this all equal to 0. Do we see how this helped us? Right? So now, what do I do? Quadratic formula? You could. You could zero product property this right now. But I would say if you continue to factor, you make your life easier by factoring. Well, magic X really only works when we have an A of 1.
Take the GCF.
There's no GCF.
Quadratic.
You all avoided this strategy like the plague.
Quadratic.
Not a long division. Give you a hint.
Quadratic. Oh, rainbow?
You said rainbow, but I said
God.
You said GCF, I think.
no. I was gonna.
Oh, okay. Okay, so what is this? This is the rainbow method, right? Now, you can use quadratic right now. You'll get the same answers, right? But watch this. This will be not that bad. So A times C is what? 6 times negative 15. That's negative 90, right? So I need two numbers that multiply to give me that. And then B is negative 1. So I need two numbers that add to give me that. So they got to multiply to give me negative 90, add to give me negative 1. Well, if they're adding, the difference between them is 1, and they're multiplying to give me 90. Yeah.
Should I treat this like a magic?
Oh, 7, 9.
No, because A isn't 1. So it would be negative 10
That's 9.
and positive 9. Negative 10 and positive 9. Okay? So those two numbers work for both. Now, what we do, this was actually our first grouping experience that we had. We said, we'll bring down the x plus 1. And then here we said, okay, 6x squared, but instead of minus x, we did minus 10x plus 9x minus 15 equals 0, right? All we did was pull apart that negative 1x into two pieces, right? And then this was our first grouping, right? Group this, group this. I get x plus 1, and then we're going to need a two parentheses situation here. What goes into both 6x squared and minus 10x? 2 and x, yep. So 2x, and that leaves me with 3x minus 5. Plus, and then what goes into both 9x and minus 15? 3, which leaves me with 3x minus 5. Now we know that in grouping we get the same parentheses twice. That comes out front, the rest goes in the back. So I get x plus 1, and then I get 3x minus 5, and I get 2x plus 3 equals 0, right? And I've factored this now. I can zero product property this and get my answers, okay? If you did a quadratic formula for this, it gets really dicey in the simplifying of the fraction at the end. This will get you right to those fractions. So what do I mean by that? Well, zero product property, right? X plus 1 equals 0. 3x minus 5 equals 0. 2x plus 3 equals 0, right? And I solve each one at a time. This one, minus 1 on both sides, x equals negative 1. This one, add 5, add 5. 3x equals 5. Divide by 3, divide by 3. X equals 5/3. Here, minus 3, 2x equals negative 3. Divide by 2, divide by 2. X equals negative 3/2. Hopefully you can see that that would be hard to get from a quadratic formula, right? You would have probably like the square root of 25 over 50. I don't know. Like you'd have to do a lot of reducing there. You can make a lot of mistakes, right? This gets you right to the fractions. Okay, why do these answers make sense? We said we were trying to find all three roots.
You can just put down calculation with it.
Well, yeah, you could plug them in and make sure it works.
Yeah.
Why did I just zoom out?
To see the graph.
Yeah. What did we say the roots were? Well, negative 1 we knew for sure. And we said this one looks like it's about what? Negative 1.5. Isn't that negative 3/2?
Yeah.
This one we said looked like it was about what?
Like 1.7.
1.7, right? Well, 1 2/3, right? 1.666, 1.7, right? So now we have the exact answers, and we're not guessing anymore. And it did give us our roots. It did give us our x-intercepts. Okay? Now, questions before I move on? Yeah.
How did you get the factor at the start of the problem?
I knew that negative 1 was a root, and therefore I knew that x plus 1 was a factor.
But we
Okay.
have to do all of that. That's way too long. like exercise like that.
What's too long?
All that.
This whole problem? Yeah, it's going to be one of your longer problems, right? I won't give you 10 of these on a test. I'd probably give you one, right? All right, now let's talk about this one. What could you do if you, like, same situation, but I haven't given you a graph, I haven't given you a root. I haven't told you, I haven't given you any hints, right? What could I do here? Anybody know? Yeah.
Rational root theorem.
Well, yes, because that's the name of the notes today, and perhaps your honors packet told you about that. But what if I didn't even know that yet?
You could just factor until you get
You could just, go ahead. What were you going to say? That you are touching on the root theorem that we're going to learn today, yeah.
massively cuts down the number.
Massively cuts down the numbers. What are we cutting down on? We're cutting down on random guessing, right? So the answer to this question, now what, is you would literally have to just guess numbers. 1, -1, 2, -2, and so on. But you are correct. There is a theorem that allows us to cut down those guesses. Yeah. So, well, first I'll show you. You guys kind of hit on a lot of the theorem and that stuff. But like, let's say we didn't know the theorem, you would have to guess, right? So you would guess. First, you would guess maybe 1, and you say, okay, let's see if this. I don't know. Maybe this is a root. Okay, and you're just hoping for what there?
You get a 0.
0, right? So we'll see if we do. Bring down the 1, 6. 12, 12. Wait, what did I do? Did I mess up?
Yeah. It has 1 times.
Oh, I'm getting ahead of myself. All right. 1 times 1 is 1. 7. I was like, the numbers aren't looking familiar from my other classes. 7, 18. Okay. Is that a root? No. Right? And what's ironic about the mistake I just made is the reason I always tell people to test 1 and -1 first is because the synthetic division is super hard to mess up. And I still messed it up. Because all you got to do is multiply by 1 a bunch of times, right? So don't do what I just did. Anyway. Okay, so that didn't work, so we keep going, right? Let's try -1. 1, 6, 11, 6. Okay, bring down the 1. I think -1. 5. I think -5. 6, -6, 0. Okay? So we can begin to factor. So we don't have to take this all the way through because I do want to get to the theorem. But essentially you would say, okay, now I know 0 equals x plus 1 and then x squared plus 5x plus 6, and I could go from there. Does that make sense? That, I would magic x. This one is magic xable, right? Then I have all my factors, I find all my roots, and I'm good to go. Okay, yeah, because that's where I want to spend most of my time. Okay, so yeah, magic x that, you'll find all your roots. Okay, let's go to the theorem, because we don't want to blindly guess, right? I would love to at least know give me some direction, okay? So for the rational root theorem, this helps us guess roots and it does so by it narrows down our possible guesses. I'm going to call them the pool. A pool of guesses are just like your options, okay? And the theorem says your possible roots are, we use the letters P over Q, and P stands for the factors of your constant, which is your last number, right? Which is what you were touching on, right? Divided by the factors of your leading coefficient. So there's actually a little bit more to it than just the constant, but a lot of times it is just the constant, but sometimes you need the leading coefficient. Okay, so if you want to just use regular language here, the constant is your last number, and the leading coefficient is your first number. So what do I mean by this? Okay. So let's say you were guessing possible roots for this next problem. And I'll throw out a scenario here. Let's say that the first root you could find was 5. Well, think about how many guesses you would have to make. It would be like 1, -1, 2, -2, 3, -3, 4, -4, 5. So that was my 9th guess, right? If we could cut that down a little bit, it would make our lives a little easier, right? So this thing allows us to do that. And let's watch. This is how it works, okay? So what's my constant here? 10, right? And then my leading coefficient was 2. So that's what's going to give me my P and my Q, okay? So my possible roots are, well, what are the factors of 10? 1 and 10, 2 and 5. That's all there is number-wise, but what about -1 and -10? What about -2 and -5? Right? So what we do is we say ±1, ±2, ±5, ±10. Okay? What are the factors of 2?
There are
1 and 2. ±1 or 2. So this is your setup, right? Now what you do is you simplify this a little bit to get actual answers here. So there's one more step where you take every one of these divided by 1, you take every one of these divided by 2, right? And that's all your possibilities. And it seems like you're going to have a zillion answers, but you'll see that some of them double up. What's 1 over 1? 1. So ±1 is our first possible root. What's 2 over 1? No, 2 over 1. So that's 2. 5 over 1, 10 over 1, right? So really you can write those first ones pretty quickly. All of those because it was over 1, right? Now, let's do it again for 2. What's 1 over 2? Just 1/2, right? So ±1/2. What's 2 over 2?
1.
We already have that. We're good. What's 5 over 2? ±5/2, right? What's 10 over 2?
5.
We already have that. Okay, so these are your possible roots, right? So think about the scenario I said where, let's say 5 was your root, right? Well, now you get to skip 3 and 4. You don't have to test those. They are not possible, all right? Somewhere in here are your possible roots. Now, this is a cubic function. Yep, cubic function. So 3 of these, somewhere in here, are your roots. They have to be in here, okay? If they're rational. Remember, it's the rational root theorem. What does rational mean?
It's like common.
It means, in everyday language, it's pretty rational. It's common sense. In math, it means can be written as a ratio. So it's a whole number or a fraction,
Oh, yeah.
right? So anything that can be written as a ratio, because you could write 2 over 1, even though it's just 2. All right, so here's the thing. You're not going to have to test all of these, right? Most of the time, you do 1, you do -1, you do 2, you do -2, and you probably found a root, and you can start factoring, and you're good, right? Maybe you get to 5, and you have to do that. You will not have to do synthetic division with fractions, but theoretically you could, okay? So, does this make sense, what we're doing? Okay, let's use it in an example, and then we'll wrap up. All right, so I'm going to skip that second one because it's just another example of the same thing. And let's use it to actually do this thing. Okay, so we're going to find the zeros here by guessing roots, but we're going to use rational root to help us guess, okay? So 0 equals 5x to the third plus 2x squared minus 20x minus 8. But before I start guessing here, I'm going to P over Q this thing. So P over Q is, well, what are my factors of 8? 1, 2, 4, and 8. So plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. What are the factors of 5? 1 and 5. plus or minus 1, plus or minus 5. I do one more step. Everything over 1 is just itself, so I can write plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, and then everything over 5. So 1/5, 2/5, 4/5, 8/5. Now, if I ask you for all the possible roots, you have to write those. Those are possible. You will never have to test 8/5 in synthetic division. But for the sake of stating the possible roots, we'll write them out. Plus or minus 1/5, plus or minus 2/5, plus or minus 4/5, plus or minus 8/5. Now, if we did this correctly, somewhere in there is our 3 roots, right? So where do we go? We start testing, right? We start testing 1, then negative 1, 2, then negative 2. Okay? What's that? Well, we're going to find all 3, but we only need to test and find 1, and then we can start factoring. Okay? So we start with 1, and then we do negative 1, right? So 1. So typically on these problems, I just see a bunch of synthetic division to get people started, right? And our problem would be 5, 2, negative 20, negative 8, and we're just interested in getting that 0, okay? Okay, so bring down the 5, multiply 5, add 7, multiply 7, add negative 13, multiply negative 13, add, who cares? It's not a root. Move on, right? Doesn't really matter if it's not 0. So we go to negative 1. 5, 2, negative 20, negative 8. Bring down the 5, negative 5. Negative 3, 3. Negative 17, 17. Who cares? Not a root, right? Move on. What's the next number? 2. Okay. 5, 2, negative 20, negative 8. I'm feeling lucky. Ready? 5, 10, 12, 24, 4, 8, 0. So it's a root. We found it. Okay, so now I take that information and I start to factor. I say, okay, that means 0 equals x minus 2, because my root that I tested was positive 2, and then 5x squared plus 12x plus 4. And this is, again, a time where I would recommend the rainbow method, okay? Watch, it's not that bad, okay? 5 times 4 is 20, and then my b is 12. Two numbers that multiply to give me 20 and add to give me 12. Because our root was positive 2. Good question. All right, so this becomes 0 equals x minus 2. And then I have 5x squared. And I'm going to write plus 10x plus 2x plus 4. Then I group these. X minus 2. 5x squared and 10x, I can pull out a 5x. X plus 2 is what's left. And here I can pull out a 2. And x plus 2 is what's left. And I'm almost there, right? 0 equals x minus 2. This x plus 2 that shows up twice comes out front. The other pieces go in the back. And I'm fully factored. I'm ready for zero product property, right? Now let's finish this and then see if these roots were indeed in our list. X equals 2, x equals negative 2, and then this one we'll do all the way. 5x plus 2 equals 0, minus 2 on both sides. 5x equals negative 2, divide by 5, divide by 5. X equals negative 2/5. Right? Okay, so those are our 3 roots. Now, take a look back 2, -2, and -2/5. Are those all in our pool? Yep. 2, -2, -2/5, right? So it does give you all the possibilities, right? And by the way, if you had guessed -2 first, you would have been fine as well. Okay? All right. So put the warm-up to the side for a moment. We'll come back to it. So for the homework, for 14, it was about types of roots, so triple roots, single roots, double roots, being able to recognize them and know what happens on the graph. And then, not forgetting how to factor and solve, but then when you get to the end of the solving, what type of roots do you have? What would happen on a graph? Could you sketch it, right? So I think we'll focus on 3A through E, if anybody wants to see one of those. And we're just going to go through the general process. So anybody have one of those they would like to see? Yeah. E. It's been a popular one today. Okay, so for E, all right, so for any of these, we're trying to find roots, right? What are roots?
Roots are the x-axis.
They're x-intercepts. They're the x values that make it true when y is equal to 0. So the first thing we need to always do is get it equal to 0, right? So if you're taking a look at this problem, you're like, well, there's things on both sides, so if I move this over here, then I'll have it equal to 0. So I'm going to add 2x squared to both sides, and I have 2x to the 4th minus 4x to the 3rd plus 2x squared equals 0. Now I ask myself, okay, what do I always look for first? A GCF. And that can involve a number, that can involve a letter, it can involve both. So what do we think could go into everything here? Yep, 2 and then x squared. So when I pull out 2x squared, I end up with x squared minus 2x plus 1. Now, in every one of these problems, really in this whole class, when you're doing steps, right, you always kind of want to have the mindset of look at it like it's a new problem every step. So for instance, here, I did this. Now, what if this was the problem that I was given right away? Oh, I would GCF. Okay, great. Now I GCF'd. What if this was the problem that I was just given right away? Started with that way, right? Oh, that's a quadratic. I guess I can try magic X, right? You kind of reset your strategies every time. So I got 1 on the top, minus 2 on the bottom. And then I say, okay, how can I multiply to get 1 and add to get -2? -1 and -1. So this turns out to be 2x squared times x minus 1 times x minus 1. Okay, can I factor further in any of these places? No, can't. Anytime I can't factor further, I say it's time for solving using the zero product property, which says make everything equal to 0, right? So I just do that, make some easier equations for myself. 2x squared equals 0, x minus 1 equals 0, x minus 1 equals 0 again. Okay, 2x squared equals 0. I'm trying to get x by itself. Divide by 2, x squared equals 0. Well, square root, and I get x equals plus or minus 0. Now, can you have plus or minus 0? Kind of, not really, yes and no. It's the same thing, but it's important because why? Why don't I just write 0?
Because you'll know that this is 2.
It's a double root, right? And that is my signifier. Now, you don't have to write plus or minus as long as you know that this is a double root, because that's important for our sketch that we're going to do. Now here, x minus 1 equals 0, so x equals 1. And then here, same thing, x equals 1. So I got x equals 1 twice. What does that mean? That's another double root, right? Those are the two ways you might get double roots. Okay, now I ask myself, what happens at a double root?
It curves.
Well, it touches the x-axis and we like to say bounces off. but it changes direction, right? It's going down and it goes up, or it's going up and goes down. So, okay, how do we sketch this? How do we go about sketching this? Well, I know some points, right? 0 and 1. I know that it's x to the 4th and it's positive, so it's going to look like that, right? So now I got to start from the top, come down, right? So if I start from the top and I come down, I head towards my first root. And when I get there, I ask myself, what happens there?
It just changes direction.
It has to go up now because it bounces. Now, how can I get back down to my other root?
Change direction.
I got to change directions again. And then when I get to that root, it's also a double root, so it bounces again. And that gives me my graph.
It bounced because it's a double root.
Absolutely, yep. Both of them were double roots, right. And if you know that, and you know what happens at each spot, it guides you the whole way, okay? Any other questions? Okay, that's your general process for these. You're going to have different factoring that you're going to need to do, GCF, grouping, all those things. But eventually you need to analyze your solutions to figure out what you got. All right, let's go to 15 if we have questions on that. So 15 was about, okay, what if you solve and you get an imaginary root? What does that mean? And then on a graph, and then how do we state our answers? How do we go all the way? So any of these that we would like to see? Sure. So number 7. Okay. So again, a lot of this is just review of factoring and solving, right? First thing I get to do is set it equal to 0. And then I look at it as if it's a new problem. And I say, okay, what if this was the start of the problem? What would I look for first? Greatest common factor. Yep. Yep. So I divide everything by x squared and I put it on the outside. I get x squared minus 4x plus 5. Okay, so I would hope that I could factor this more. So I would do magic x, or b squared minus 4ac, and I get 5 on the top and minus 4 on the bottom. What would I discover? You can't do it. This doesn't work. Right? So, okay, we're stuck here if we were just remembering steps. This is why I always try to hammer, like, know the property, know what we're doing, and then you'll know a route, even if you get to a problem that's a little different, right? Because what do we have here? Well, we factored, and we can't factor further. Anytime we factor, and we're equal to 0, and we can't factor further, what do? We solve by, well, before that. Why can I use that? It's the zero product property. Things that are multiplying to give you 0 must each be set equal to 0. So what's the first thing that's multiplying to give you 0? X squared equals 0. What's the second thing that's multiplying to give you 0? This whole thing. So x squared minus 4x plus 5 equals 0. I can do both of those, right? I have to remember from that unit how to do them, but I can do both of those. This one we already seen, square root, x equals plus or minus 0, double root, right? That one, I can't factor it. I have a way to solve quadratics when I can't factor it, and yes, that's the quadratic formula, right? So I go ahead and I set it up. X equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. It always looks like a mess at first, and then we clean it up a little bit, right? X equals 4 plus or minus whatever that is under there over 2. Now, what is that under there? Negative 4. Yep. So it's negative 4. Okay, so at this point, you've got it simplified, but not all the way, because we don't leave a square root under a negative, and we certainly don't leave a perfect square under there. Okay? So if you can see it, go for it, but if not, take it over to the side. Say, square root of negative 4. Well, I know I can break that apart. That can be square root of 4 times square root of negative 1. What do I know negative 1 actually is? Square root of negative 1. I. what do I know square root of 4 actually is? Plus or minus 2. So really what I have is plus or minus 2 times I, or plus or minus 2i. So if that's true, it goes right in that spot, and I end up with x equals 4 plus or minus 2i over 2. And the very last thing I check for is, can I simplify this? Because, like, fractions ask you to divide, right? Can you divide this? Can you divide that by 2? Yeah. So what happens?
The 4 would become 2.
4 divided by 2 is 2.
And then it would cancel.
Yeah, these other 2's would divide into 1, and you'd end up with 1i, or just I. Okay, so if you had this situation, you got a double root here, and you have 2 imaginary roots here, that should make you feel good because you started out with x to the 4th, right? And you could probably even sketch this, but I didn't require that, I don't think. No, so no worries there. Okay? Make sense? Yeah, what's up? Oops.
No, I don't really think so. But how do we sketch an eye?
How do you sketch an I? Well, is I a real number?
No.
No. So would you get an x-intercept?
No.
No. So if you had this situation, you know your only x-intercepts are what?
0 and that's it.
Double root of 0, right? So, and you know that these things typically look like this if they are like that. So what do?
You would start from the top, and then you would go to 0, double bounce.
So, okay, we start from the top,
You would start from the top all the way to 0, and you would
bounce.
bounce again, and then
But yeah, I was
bounce.
gonna say no.
So this is, remember, these don't have to be symmetrical. This is maybe something we haven't really covered yet. I know it's got to bounce at the 0, right? I know that it can't cross before that or anything because that's my root, and then it must come up there. Now, it also could have gone like this, right? And that's beyond our knowledge, right? But this would be an acceptable sketch, yeah.